Okay, we're gonna hop to it because the sooner I do that, the sooner we can be done all of our topics, and then the sooner we can have a work period, etc. So because of that, no, nothing new. Actually, I guess I forgot to mention this in my other class. There's only one more quiz. This is the last one. There won't be one next week because there's a chapter review assignment, and why would I give you at this point in the term? Why give you both? Like, what's the point? So that'll just be due whenever it's due. So last class we spent most of it talking about row reduction. We did a bunch of examples. Specifically, we did at first examples on just how to do the process, but then we said, hey, we can use that to solve systems of equations. And so that's really what we did, right? We did a bunch of examples of that, just going through the process and sort of demonstrating that it is just an algorithm, right? There's this sort of a methodical process that you go through each and every time. And it is one of those things where once you do it once or twice, you're like, okay, got it. And then it's just arithmetic mistakes. It's common. So the way we use it to solve a system of equations is first we find this, what's called the augmented matrix, where you just read off the matrices from the system of equations, right? It's just read it off. Nothing too fancy there. Then you do that row reduction step to, it's most of the work, reduce it to that reduced row echelon form. So you got that staircase shape, and then you got zeros below those leading entries and zeros above. So the process is create zeros below by going down like that. And then once you get here, reverse it, create zeros above by going backwards. And then you have something that looks really nice. And once you have that, all you do is say, hey, that still represents a system of equations. You write down the system of equations, and usually it's almost immediate to have the answer, right? Either you'll look at it and you'll be like, hey, wait a minute, this doesn't make sense. I got 0 equals 3, so there's no solutions. Or you'll look at it and say, oh, it tells me that x is this, y is this, and z is this, done. Or you'll have an extra free variable, in which case you would have 3 equations and 4 variables, in which case you just have to say, okay, whichever variables weren't my leading ones, so those ones that I've been circling, you'll have like that sort of gap there. You just move that to the other side, and then you're done. Right? You say, hey, you could pick that to be whatever you want. So once you get to here, it's already almost done, basically. In 2 out of the 3 cases, there's nothing left to do. In the remaining case, you move some stuff over, and then you're done. So the way I'm going to do this today is I want to start talking about the next topic, which is just matrix operations, things that we can do to them. And then at the very end, I'm going to be like, okay, I just crammed a bunch of new math into you. Let's go back and do an example of this so that you're warmed up for quiz and whatnot. So we're going to talk about matrix operations, just like we did for all the other objects we studied. We said, hey, what can we do to this thing? We got this new object. Let's play with it. So the first thing I want to talk about is the idea of a diagonal entry, because we often talk about them. They come up a lot. And it's kind of exactly what you'd expect it to be. You need a square matrix. The diagonal entries lie along what's called the main diagonal, which is best seen as an example. So you've got our favorite little matrix that I keep writing down. This thing. So the diagonal goes from the top left down like that. So the diagonal entries in this case are 1, 5, and 9, right? And so the notation we use for this, well, for entries in general, is something like this, right? This is the matrix A. And this is saying, hey, this says the number in row I and column J. So we can write down these diagonal entries pretty easily. It's just when these two numbers are the same thing, those are diagonal. So these are the same. So as an example with this matrix, A1, 1, row 1, column 1, That's this number. A22, row 2, column 2, that's 5. The third one, row 3, column 3, that's 9. All right, so this is just telling me what row to look in and what column to look in, and boom, there we go. And the reason why this notation is used is, well, in math, we like to index things a lot, but for programming and computers, they also like to index things a lot, right? You've got arrays. So you index arrays using indices, and you can iterate those over with loops, right? So, you could say for every row, which you would say for I in length of that thing, and then for j in length of that. So number of rows, number of columns, right? And then I is your row that you're currently looking at, j is your column you're looking at. Okay, so a diagonal matrix is zeros everywhere except possibly these diagonal entries. So something that looks like this. Got zeros everywhere that isn't that diagonal. And then we got that diagonal. And we just put numbers there. We can say 1, -2, and it says except possibly those, so we could put a 0 there, right? That's fine. It's just, these are the only places that if they're not 0, they lie along that. Okay, so that's just an example of a matrix that comes up pretty often, specifically with something called diagonalization. If you're looking at transformations, you would care about that a lot. So if you're interested in physics in computing, you'll come across it. There is a specific diagonal matrix that we care about, though, a lot, and that's called the identity matrix. And that name is because when we're talking about the number 1, that's called the identity for multiplication. It just behaves like 1, right? It does nothing, basically. So we're going to try and do the same thing here. So for the operation of matrix multiplication, this will also do nothing. So the notation we use is IN if we need to specify the size. Sometimes we don't need to. So let's talk about I3. Or let's do 4. So this is the diagonal matrix that's 1s all along here and 0 everywhere else. So it'd look like this. 1, 0. So it's 1s along that diagonal, 0 everywhere else. 1 along diagonal, 0 everywhere else. And this matrix ends up, in a way, working exactly like 1. Okay, there's one other type of matrix that we would care about a decent amount, and this is the 1. We also have a 0. So 0 matrix. It's just the matrix with all zeros. So the matrix with all 0. Every single thing in there is a 0. So the notation, unfortunately, is 0. Indistinguishable from the number 0, but context will usually make it obvious. If the context doesn't, then we sometimes might write the size of it. We'll say it's the 3x2 0 matrix or something like that. If we need to specify, like if we had, somewhere blah, 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 and then we had this number 0 written down, we might want to be like, hey, that's a matrix, by the way. But generally speaking, we don't have to carry too much about it. So an example for 2x3, so 2 rows, 3 columns. Bam, it's just zeros, right? Okay, so this, we're calling it the 0 matrix because it also behaves like 0 for the operations where it would matter, right? So we've got some multiplication, we've got addition. For addition, this does nothing, etc. So that's why we call it that. So now let's actually talk about some of these operations we can do on matrices. And maybe this isn't necessarily an operation, but if we have two matrices, we need to be able to say when they're equal, right? So two matrices are equal basically exactly the way you would hope, right? Two vectors were equal if just you went down them and all of their entries were the same. Same thing for matrices, right? We just compare them, the entries, we go along them, they better all be the same. Two matrices are equal if their entries are the same. And this sort of comes from that automatically, but there is something that we should explicitly say. They also have to have the same size. Right? It doesn't make sense to compare two things that are a different size, right? Like this thing, is this equal to this? Well, they don't even have the same number of numbers, right? So it doesn't even make sense to ask if they're equal, because how could they possibly be? This has 9 numbers in it. This has 6. They can't be equal at all. So just as an example here of what I mean, to get used to it, 1 for x, y equals 1 for minus 2, 1. So these have to be equal in terms of all their entries. So top left ones have to agree. Top right ones have to agree. That means x has to be minus 2. Bottom lefts have to be the same. Okay, good. Bottom right have to be the same. Y has to equal 1. Right. Again, that's sort of a rudimentary quote-unquote equation to solve, but it just emphasizes what equality means, right? We just compare them across like that. Okay, that's good, because that just basically means equality is exactly what you would hope it to be, right? You just sort of just compare them how you would hope. So what about addition? Good news. It works how you would hope it would. So for vectors, when we were talking about addition, we just said, hey, just add them up component by component, right? Just go down the list and just add them up. Same thing for matrices. For matrices, we add them entry-wise. So just go down the list. As a remark, of course, they must be the same size. This is actually a common mistake that students will make, because you're not used to being able to say no to a question and have it be the right answer. Like if I say, add these two matrices if possible, that if possible means you might be able to say, I can't, right? That is a correct answer sometimes. So if they're not the same size, you don't have to still somehow force addition to happen. You could just say, hey, they're not the same size. No, I won't be adding them because I can't. So we do have to have them be the same size. So let's just do a quick example. 1, 2, 3, 4, 5, 6, 7, 8, 9. My favorite matrix to write down. And then, who cares? 1, 0, minus 2, 3, 1, 4, minus 1, minus 1, 2. Okay, sure. Random matrix. So what this is saying is we just add it component-wise, right? Or entry-wise. 1 plus 1 is going to be that top left entry. 2 plus 0. 3 minus 2. 4 plus 3. 5 plus 1, and so on, right? We just keep going. 6 plus 4. 7 minus 1. 8 minus 1. 9 plus 2. And now we just actually do it. So that's 2, 2, 1, 7, 6, 10, 6, 9, and 11. Just add them up. And so looking at this, it kind of makes sense that if they don't have the same number of entries, we can't meaningfully add them, right? If I instead said, okay, now add these. This is the mistake that students make, because they're like, okay, these are zeros then. Why? Why are they 0? Why aren't they 1? Why aren't they 5? Like, why did you choose 0? Because they're empty. Empty in mathematics is not this. Nothing is not the same thing as 0. 0 is a quantity. There is 0 of those things. Nothing being there means there is nothing there. It is meaningless. There is nothing there. So the problem is, because we erase it like that, it's actually like this. They don't even have the same shape, right? So it doesn't make sense to add them. So this is what I mean by students will frequently force the addition. If you run into that, they're not the same size, you just say, no, I can't. You do not have to add them. You just say, no, it's not possible. They're not the same size. Okay. So something else we can do to matrices. We can do scalar multiplication. And that's something that we could do with vectors. And this makes sense, because what is a matrix? It's a grid of numbers. What is a vector? Well, it's ultimately a grid of numbers too. It's just we've decided to write them a specific way, right? There's either it's just a column or it's a row. We're saying, hey, matrices are just that with but maybe more than one row or more than one column. So all the same things that we can do to vectors, we can do to matrices. So we do this same as vectors. Multiply every entry by the number. Right, so you have something like this. I'm just going to write down as 5. 1, 2, 3, 4, right? Okay, so we just multiply all the entries by that number. 5 times 1, 5 times 2, 5 times 3, and 5 times 4. So this ends up being 5, 10, 15, 20. Bam, done. So again, this isn't a surprise, right? We define this for vectors that works very similarly. It's just we have more numbers to worry about. What about subtraction? Well, I don't even know if it's worth mentioning, because how do we do subtraction? Exactly how you would expect, right? We take this thing and now we subtract entry-wise, right? It's exactly the same as you would hope. So it's not entirely worth, spending too much time on. But there are a couple of new things we can do with matrices. So just like with vectors, where we were like, okay, we can add them and we can multiply them by numbers. That kind of makes sense. And then we said, hey, there's a new thing we can do. We can do this thing called a dot product. So for matrices, there's actually quite a few things that we can do operations-wise. But an easy one to talk about is something called transpose, which sounds like a big fancy math word, but the process is fortunately very simple. So the transpose of a matrix of a matrix A denoted it looks like it's to the power t. It's not a power. It's just saying, hey, do this. It seems like, hey, well, wouldn't I get that mixed up? No, I've never seen it happen. Context makes it pretty obvious, because we would use like n for a power, like little lowercase n, just like we normally would for matrices. So this symbol is exclusively for this operation. So what is this? Is the matrix where we swap the rows with the columns and the columns with the rows. Where we swap the rows with the columns and the columns with the rows. That actually even sounds like a pretty straightforward thing to do. And it when you actually do it, it's totally fine. So let's say we had the following matrix, 5 minus 2. And we want to transpose this thing. So what do we do? Well, I would say you just pick either the rows or the columns. It doesn't matter which one. I'm going to pick the rows, and I'm going to take the first row, and I'm going to write it as the first column instead, right? Because we interchange the rows and columns, so that means the rows will be the columns. So 1, 2, 1, 2, minus 1, 0, minus 1, 0, 5, minus 2, 5, minus 2. That's it, right? And it's just, we basically take the matrix and sort of flip it in a way, right? It less flipping, more mirroring along sort of a diagonal here. So like this will flip down like that, this will flip down like that, and this will flip down like that. It's easier to see when it's a square, where you just sort of draw along the diagonal and you flip around it. But when it's not square, it's a little weirder looking. But this process will work either way. You just say, hey, I'm going to take the rows and write them as columns in order. And that's fine. So this ends up being a useful thing, again, with transformations and stuff, because we have what's called a symmetric matrix. So let's take a look at one real quick. 2, 4, 5. And I gotta think really hard here. So something like this. So this is called symmetric, and it even makes sense in the definition. If we draw along this line like this, if we were to transpose this thing, we get the same result, right? Nothing happens, right? So if we swap the row, the first column would be this row, 1, 2, 3, 1, 2, 3. Oh, same thing. Second row becomes second column, 2, 4, 5, 2, 4, 5. Oh. Third row becomes third column, 3, 5, 1. Oh, they're the same. Right, so if we transpose this thing, we get back where we started. And that's called a symmetric matrix. There's a lot of algorithms and results that work really nicely if you have matrices that look like this. So that's the power of this, right? It's a really simple thing to do, but it turns out a lot of really useful matrices have this property. But nicely, this isn't too hard to compute, right? You interchange rows and columns. Not too bad. Okay, well, let's talk about the elephant in the room. We need to talk about multiplication of matrices. And you might look at it and be like, hey, wait a minute, Travis, though. The whole reason I said for vectors, we can't define multiplication, and why the dot product isn't multiplication is, well, the dot product of two vectors is a number, right? So we need multiplication to produce another vector. So this is going to be an operation that takes two matrices and produces a matrix. And generally with multiplication, when we're talking about just numbers, right? What is multiplication really? So if we're talking about, 5 times 2, what is that really? It's repeated addition, right? 5 times 2 is 2 plus 2 plus 2 plus 2 plus 2, 5 times, right? You add that up, you get 10, right? That's what it is. So we could say, well, why don't we just do that for matrices, right? Why don't we define multiplication to be that? So if we defined it to be repeated addition, you would take this matrix and then add it to itself, and then again and again. You combine that up, what you actually got was 5 times that matrix, which is just this, right? That's scalar multiplication. So that same motivation, let's just repeatedly add matrices, gives us something that we already have. So that's not the right definition for multiplication. And that doesn't even really work anyway, because we would expect multiplication to be two matrices times each other. This is a number times a matrix. So it also doesn't really match up. So good news and bad news. Matrix multiplication looks really bad initially, because I'm going to state it in several different ways. The first one is going to be the formula, like a mathematical formulation of it. And you'd be like, Travis, that looks awful. Why are you writing it that way? Because you're programmers or future programmers. And the way it is written is really, really useful for implementing algorithms with, because it's going to be some indexes or indices. And those are useful because if you want to iterate with a loop, you go over indices like that. So we're going to start with that definition. So if A is an M by R matrix and B is an R by N matrix, so they do have different sizes, but just like with the other ones, we will have a size restriction. They do need to match up in a certain way. The product is a matrix C. It turns out it's M by N, whose ijth entry, I know that's sounds like a mouthful, but it's just saying, hey, pick one of these entries, right? We're indexing it with row I, column J, right? Remember, this is row, and this is column. Okay, what does it look like? Well, it's going to be a number, right? Because it's just a single number in a matrix. And we sort of have, it's just a bunch of addition. It's multiplication and addition, just like the dot product, it turns out. And there actually is a connection here. So I need to look at my sheet so I don't screw up the indices. It's AI1, B1J plus AI2, B2J plus AI3, B3J, and you just keep going until you get to R. So first of all, that looks like a pretty messy definition. We're going to work with it a little bit, but right off the bat, I think you can kind of see why it would be useful for programming, right? Because we have, if we wanted to iterate over this, we're going to say, okay, I'm going to go over the rows of my matrix, which I'm going to call I. And for those rows, I'm going to also go over the columns. So like, let's say I picked this row, and now I do column 1 of that row, column 2 of that row, and so on. I'm going to call that J. And then I have these extra numbers here, right? We've got this 1, this 2, this 3, and so on. And that's another loop. So you've got 3 loops like that, right? You just need 3 variables that you iterate over. But you can kind of see how this like if you have a grid of numbers, 2 grids of numbers, then this is just, you plug it into basically your for loop, and you can plug in this formula almost exactly, right? And it'll work out really nicely. So that's why I write down the formula, right? It's not to just be like, oh, let's look at the awful thing. It's because if you actually implement this in Python, say, this is a useful way to read it. But we'll do an example, but there's one thing I do want to talk about here, and it's that there's a size requirement, or let's say constraint. We actually need some sizes to agree here. So, we don't actually call it C. We call it exactly what you'd expect, A times B, right? So this is an M by R matrix. This is an R by N matrix. And one of our requirements is that these sizes here, the inner ones, we call them, they have to be equal, right? So inner sizes have to be equal to each other. And if we look at this formula, that kind of makes sense, because what is it saying? Well, the R here is this inner size in both of them. And if they weren't the same thing, like if the one for A was different from B, then if we go through this formula, we're going to run out of numbers for one of them eventually, right? Like let's say this was a 3 by 4, and this was a 2 by 3. Then sure, we have 4 numbers to write down here for A, and we only have 2 for B. So we're going to go through the formula and be like, oh, we ran out of numbers. This doesn't make any sense, right? So it makes sense that we have to have this agreement here. And then when I actually show you how to do this, as a human being, this is good for computers, but we're not computers. You'll also see why they need to agree there. And we also said that it's an M by N matrix, the result. Well, conveniently, those are the outer sizes, right? That's the size. So we need these to sort of match up for it to make sense. But okay, let's actually just do an example. And this example, we're going to use this formula at first, but we're going to also show you a visual way to do this and then just move away from the formula, because the visual way is, generally speaking, how you do it. And then when you become a masochist like me and do so much math, You don't even need the visual anymore. You just do it in your head, and then it's like, that's horrible. So actually, in my class, the last one, I used these numbers. So I was like, wow, this is really awful. These numbers are huge. So I'm going to write down different numbers than what I have here. Put same size. 1, -1, 2, 2, 1, 0. Okay, so first thing we should do, and this is true in an algorithm too, we should check, do the sizes match up, right? That's something we say, hey, these need to match up. So this is our matrix A. This is our matrix B. This is a 2 by 2 matrix, 2 rows, 2 columns. This is 2 rows, 3 columns. Good, they're the same, right? If they're not the same, we don't even bother going any further, right? We just say, nope. And this is another example of sometimes the correct answer is I can't do it, right? If these don't match up and I said, find the multiplication if possible, they don't match up, you're like, no, there's nothing to be doing. And it's the easiest mark you've ever got in your life because you just say, I don't have to do anything. But they do match up, so we have to actually go through the process. So, okay. We're looking for this first entry here, this top left one. So let's digest this formula a little bit. So we're looking for the 1, 1 entry. So remember, this is I and it's J. Grab some different colors, which will help. So this number here is I, and this is J, right? So we're going to go ahead and just plug into this formula. I is 1, and J is also 1. So A1, 1, B1, 1. Okay, that's nice. That's just all 1. Oops. And now we do the second one. So I and J stay the same. So I is 1, J is also 1. But now we move to 2. And we just increase that by 1. So, okay, this is still, we got so many indices here. It's a lot to sort of digest. But what this is saying is take the first number in the number in the first row and first column of A, that's this guy, and multiply it with the first row and first column of B. That's this one right here. Okay, so that's going to be 1 times 1. What is this saying? It's saying in row 1 and column 2 of A, multiply it with column 2, row 2, column 1, this guy. So 2 times 2. But this ends up being not so bad because we're looking for this entry right here, which is row 1, column 1. So in this left matrix, we go to row 1, and in the right matrix, we go to column 1, and then we can just move our fingers. It's this times this added together. Right? That's what the formula tells us to do. But there's a nice finger movement we can do to actually compute it. So this one ends up being 5, so we write down 5. But now let's do the next one. So this is going to be C1, 2. So same thing, except now this number is 1 and this number is 2. A1, 1, B, 1, 2. I'm writing down the formula, but again, we're going to move away from it. So don't worry too much about it. This is what the formula tells us. Now let's digest what it just told us. This is saying row 1, column 1 of A, so that first top left entry, times row 1, column 2. So that's 1 times minus 1. Then it's row 1, column 2, that's this guy. Row 2, column 2, this guy. So again, we just said this times this plus this times this. So we have this sort of finger motion here, right? We move across like that. So then this is 2 times 1. So this ends up being 1. And that's actually how we want to do matrix multiplication as people. We don't want to worry about this formula so much. This is me just saying, hey, we wrote down this nasty looking formula, which is great for computers, but there is a nice methodical way to sort of move through it visually that does the same thing. So let's take a look at this one. So this is column 2, and this is column 3 of our resulting matrix. So you grab whatever row you're looking at, you grab that row from the left matrix, and whatever column you're looking at, you grab that column from the right matrix. So we're looking at row 1, column 3 for this entry, row 1 of the left matrix, row 3 of the right matrix, and we do the finger thing. 1 times 2 plus 2 times 0. So 1 times 2 plus 2 times 0. And now we sort of just keep doing this, right? This is row 2. This number right here is row 2, column 1. So we grab row 2 from the left matrix, and we grab column 1 from the right matrix. And then we do the finger thing. 3 times 1 plus 2 times 4, 4 times 2. Like that. And rinse and repeat. Row 2, column 2, row 2, column 2, 3 times minus 1 plus 4 times 1. And the last one, row 2, column 3, 3 times 2 plus 4 times 0. So I want to focus, and when I'm doing further examples, we will focus on doing the finger thing, right? That's the more important thing to take away from this, except for algorithms. We want to do that, potentially. So at the end of the day, what do we actually get for the result of our product here? So 5, 1, 2, this is 3 plus 8, so 11. That's minus 3 plus 4 is 1, and that's 6. And that's the product. So this is another one of those things, just like row reduction, where the first time you see it, you're like, oh God. And then you actually do it a few times, and you start to get into the habit of moving your fingers along like that, and then it starts to become second nature, because it is a very mechanical process, right? You just do that a bunch and write down the numbers. Now, it's okay to do this too, especially because it's so easy to make arithmetic mistakes that I actually, you could just write it down on the side or punch it into your calculator or whatever you need to do the arithmetic, so that you don't make a mistake. Once you do it enough times, it does become possible to do it in your head, but it's nice to just write stuff on the side. Okay, so there is another way to view multiplication, and it has to do with the dot product. So really what we're doing here is a bunch of dot products, if we think about it. This is row 1 dot with column 1, right? That's what that mechanical process is. So that gives us an alternate formula for matrix multiplication, which some students have looked at and they're like, oh, that one makes sense to me. And then they just do that. And that's totally okay. So suppose we have some matrices A and B. And so we're going to write it like this. This is row 1, row 2, row 3, and there's some number of rows. There's m different rows, right? So this is not a number. This is now, it's a whole row. And we're going to multiply this with B. Instead, we're going to write this as columns. Column 1, column 2, and so on, column n columns. Now, if we want to actually do this product, we're going to take row 1 and column 1, and we're going to sort of do the finger thing along it, right? But another way to write that is row 1 dot column 1, right? And this is now a formula, right? It's just something you can do on the side. You could say, okay, well, I wrote row 1, and I know column 1, so I do the dot product on the side. And then you can just sort of rinse and repeat, right? This is row 1 dot with column 2, row 1 dot with column 3, and you just keep going, right? Row 2 dot with column 1, row 2 dot with column 2, and so on, right? You just fill out that matrix. And so in the past, I've had some students, I explain it this way, and they're like, I like that because it's formula, right? I just do each of these individually on the side, right? And that, pick your poison, whichever one you like the most. Okay, so with that said, that's probably enough of that for now. So we're going to move into just like an example because, you know, I talked about a bunch of new math and there's a quiz and now everyone's like, so I'm just going to do an example of what's on the quiz so that we're warmed up and refreshed for it. So is X a linear combination of the vectors v1, v2, v3, and v4? Well, we need to write down what those vectors are. So X is this, and v1 is the following vector. I just have to copy stuff down. v2 is this thing. v3 is this thing. And v4 is this thing. Okay, so we got these vectors. So this is kind of what linear algebra ends up being like most of the time. There are like 3 operations you do in linear algebra. Like I took 3 different courses in this that built on each other, and ultimately there was 3 things I did. Row reduction, matrix multiplication, and something called determinants, which we're not going to talk about, so don't worry about that. But those are the 3 things I spent most of my time doing. So it all boiled down to a bunch of terminology and applications of that. And so it was just digesting what the words meant to figure out which of those things I needed to do, basically. So what that ultimately means is you flip back and you look at definitions. You're like, what does that definition mean? And then you write it down and you're like, okay, I know what that definition means. Now that helps me solve the problem. So in this case, we look at it, it says, is X a linear combination of these vectors? And then you're like, oh, what the hell does linear combination mean? And you look through your notes and you say, oh, linear combination means X has to equal some number times v1 plus some number times v2 plus some number times v3 plus some number times v4. Right? So can we find A, B, C, and D so that this is true? This equation is true. So we just want to solve for these variables, right? A, B, C, and D. Well, right at the moment, we look at it, we're like, hey, you know, I don't know how to solve vector equations, right? That's weird. So let's see if we can, you know, sort of simplify this a little bit. So we know what all those vectors are, right, in that equation. So we've got X, which right there, actually, I'm going to write it, I'm going to do this. Makes our life easier. I'm going to X the other side. So first, we've got that number A, which we don't know. That's the thing we're trying to find out. We don't know what that is. Times that first vector, minus 2, 1, 1, plus B times that second vector, 2 minus 1 minus 1 plus c times that third vector, minus 1, 2, 1, plus d times that fourth vector, minus 1, 3, 1, has to equal whatever x was, minus 1, 2, 1. All right, we're cleaning up the sauce a little bit, right? We got rid of some of the, symbols. We got actual numbers now. But we still don't quite know how to solve this yet, so there's still more we can do. These are all vectors being multiplied by numbers and being added up, so let's just crunch it all together, right? Let's combine it all together. So if we combine all this together, we're going to get minus 2a plus 2b minus c minus d equals minus 1, 2, 1. Then the next one is a minus b plus 2c plus 3d equals 2. A minus b plus c plus d equals 1. Hey, wait a minute. This looks like a system of equations, right? This first one is a bunch of stuff in variables equals a number. Minus 2a plus 2b minus c minus d equals minus 1. A minus b plus 2c plus 3d equals 2. And a minus b plus c plus d equals 1. And that's just from properties of vectors, right? They equal component-wise. But now this is a system. And we spent a painstaking amount of time talking about how to solve them. So step 1, we find that augmented matrix, which is just reading off our equation. So we've got minus 2, 2, minus 1, minus 1, minus 2, 2, minus 1, minus 1. We draw that bar, and then we do the other thing on the equal sign. Next row, 1, minus 1, 2, 3, and we write down a 2. 1, minus 1, 1, 1, 1. And now we're just doing the mechanics, right? We're just going to crunch some numbers. So we're going to do that row reduction. So as a reminder, our goal is we want to ideally put a 1 up at the top left. That's the first step of our process. So there's a couple ways to do that. You could divide the first row by 2 or minus 2. That's going to have fractions, so it seems like a bad idea. It would work, but I wouldn't recommend it. So we could just switch one of these with the first row, and it doesn't matter which one. So let's pick the bottom row because it's just ones. That looks nice. Row 3, swap with row 1. Okay, so what do we get? 1 minus 1, 1, 1. We didn't touch row 2. It's 3. And then we swap this down here, minus 2, 2, minus 1, minus 1, minus 1. And now we can do our process, right? We're going to say, all right, I got my nice looking 1. I'm going to use it to make zeros below. So that means we're going to take row 2, and we're going to subtract row 1. And row 3, we're going to add 2 times row 1, because that turns this into a 0, right? Now, this is an important reminder. We are adding the entire row. We are not subtracting 1 from the row. We are not adding 2 to the row. We are taking this row and bringing it down entirely, right? Like that. So that's a common mistake to make is just subtracting the number from the row. But this is an equation. So let's just say we had x plus y equals 1. If you just add 1 to the row, then you actually change the equation, right? That's a bad example because it doesn't change the solution. let's say we had 2x plus 3y equals 1. Right? If you add 1 to it, you get 3x plus 4y equals 2, which is a different equation, right? So be careful with that. Remember, we're dealing with the row. You're taking this row and adding or subtracting it to the one below. So let's go ahead and do that. So we're subtracting from row 2. We're taking row 1 and subtracting it. So 1 minus 1 gives us 0. Minus 1 minus negative 1 minus 1 plus 1 becomes 0. 2 minus 1 is 1. 3 minus 1 is 2. 2 minus 1 is 1. And now we go to the next row. Row 3 plus 2 times row 1. So minus 2 plus 2 times 1, 0. 2 plus 2 times this gives us 0. Minus 1 plus 2 times this. So that's 2 minus 1 is 1. Minus 1, same thing. Plus 2 times that is 1. And these are all the same numbers. Awesome. Now we just keep going. The next step is cover up the row we just dealt with and do the same thing. Right? Take the leftmost thing, that's this number here, make it a 1. Oh, cool, it is a 1. And use it to make zeros below. So we can say row 3 minus row 2. Right? That'll make a 0 there. 1, 1, 1. 0, 1, 2, 1, 0, 0. Now this becomes a 0 because we're doing this row minus this. 1 minus 2 is minus 1. 1 minus 1 gives us 0. And then we just keep going, right? At this point, now we cover both of these up and we say, okay, do the same thing, but there's no zeros to create below. So that means the next step is to sort of reverse our process and create zeros above. We should also multiply this row by minus 1. So I'll write that down. Row 3 times minus 1. I want to write the matrix up here. 1 minus 1, 1, 1, 1. 0, 0, 1, 2, 1. Like that. So now we're going to take this and use it to create zeros above. We start at the bottom right and work our way up. So that means row 1, we're going to take away row 3. Row 2, we're going to take away row 3. 2 times row 3. And we're just going through the motions now, right? 1 minus 1, 1. That's a 0. 1 minus 1. 0 minus 1 minus 0 doesn't do anything. 2 minus 2 times 1 gives us 0. So this is 0, so nothing happens. And now we're almost done, right? It's looking pretty nice. We cover up that bottom row and do the same thing. We look for the next row up, take the leftmost non-zero thing. This one, create a 0 above. Row 1 minus row 2. 1 minus 1, and that's going to be 0. This minus this, it's 0. Like that. Got that nice staircase shape. Zeros above and below. Looking pretty simple. Now the last step is just reinterpret it as a system of equations and solve, right? That's it. But we don't actually even need to do that because this question just said, is it a linear combination? And the answer to that question is, can we find those numbers at all, right? Can we find A, B, C, and D? Well, at this point, well, yeah, it doesn't matter what the numbers are, right? Because it's just going to say this is A minus B equals 0. C equals 1 and D equals 0. So that means A equals B, C equals 1, and D equals 0. So pick your favorite number for B, right? So A equals 2, B equals 2, C equals 1, D equals 0. There we go. Those are the numbers that will make this work. And we can double check it if we want. Assuming I didn't make an arithmetic mistake, please don't check. Because I might have, I was doing this in my head. But the point is now we can actually plug those numbers into this and it should work out. And that's it. So as a heads up, when you're working on these types of problems, two things. One, take a look at this matrix we have here. That first column is just this first vector. That second column is the second vector. Third column, third vector. So you could skip all this and just write that down if you can spot that, but you can write this down too if it helps. That's fine. But this is the bulk of the work, is just doing this. I am not here to test your arithmetic skills. If you make a mistake adding 1 to 3 and you write down 3 or something, I do not care. I will still give you most of the marks if you didn't make any massive conceptual errors here. There's a couple of very common mistakes I'm looking for, and by common I mean like in a room of 40 people, like 4 people will make the mistake. The vast majority of people do this correctly, minus some arithmetic mistakes, or you copied something down wrong, right? That's about it. So if all you did was you made an arithmetic mistake and did everything else correctly, then as far as I'm concerned, you did the question correctly, right? You weren't a good enough computer is what making an arithmetic mistake means. And like, no kidding, you're not computers, so that's fine. So I just don't freak out if you make an arithmetic mistake is what I'm getting at, which it doesn't matter how many